Okay, good afternoon, everyone. Let me start my timer. Okay, thank you for the introduction. Indeed, I'm an assistant professor lecturer, as we are called in the UK, in Mechanics of Advanced Materials Research Group. Today, I'm going to present the work of our PhD student here, MD Niamul, on dynamic fracture of additively manufactured composites. A bit of background. I know there are lots of talks, so bear with me for a moment. Why we care about AM, obviously, is the ability to produce complex architectures at will, like you see even like commercial brands coming with glasses or whatnot, artistic things. Rapid prototyping, reduced material waste. It's cost effective, at least that's how it has been claimed. And some people also use it for creative art. This is well-renowned sculpture. But I know yesterday in the plenary we had a discussion that there's not enough results on fatigue. I would claim we should add that there are not enough results on the dynamic performance of additively manufactured polymers. So typically what we see is tensile test, quasi-static test, and that's it pretty much. So let's have a bit of background excursion here. So most of the studies are basically parametric, identifying influence of printing parameters, for instance, different lathe height, different infill densities, different patterns, and come up with some results for the impact force. And then we have identified some results of dynamic compression right there, and also results for the effect of different shape. Probably you can't really see, but the building blocks of these structures are quite different. That is for pure polymers. In this case, it could be ABS, could be PLA, and so on. If we move to the regime of additively manufactured polymer composites now, there are studies, again parametric studies, on the effect of different type of fibers. For instance, here on the left, we see different structures comparing the effect of carbon versus Kevlar fibers. And again, we can discuss about volume fractions and so on. On the right, we also have identified some literature studies on the impact resistance for different architectures, and a lot of these are inspired by nature, as we can see here. So at the end of the day, why should we investigate the dynamic performance of these additively manufactured materials or components? Obviously, we need to expand, to broaden the application to this regime of dynamics. For instance, you see here some prosthetics. I would say these need to perform well in such tests. And this is another study to create armor based on these composite materials. Not to mention any application, any potential application on aerospace industry, and so on. Our research approach, obviously this is the end result here. Sorry. This would be the end result. Analyze the dynamic fracture behavior with a variety of tests, and also have a validated finite element analysis model to get away from really printing more material and performing really in vitro experiments. Before I go to the test, a few words about the materials. So you see here we have chosen nylon, we have chosen carbon fiber, so this would be our composite. The reason for that is, if we see at these highlighted blocks there, that nylon as a matrix seems to be performed better than ABS or PLA in tensile, impact resistant. Okay, maybe it's comparable to ABS. And carbon fiber as well, it's higher, performs better actually than Kevlar or fiberglass. Okay. The approach we took was to construct two different structures. One would have short carbon fibers, and this comes from the manufacturer as is. And in this case, the volume fraction is set at 20%. There's nothing we can do. Another aspect there, obviously, is that these fibers are not oriented in the way we want. There are lots of studies trying to identify the orientation distribution and so on. On the other hand, with the continuous carbon fibers, we have fixed, in this case, the volume fraction at 10%. So bear this in mind for further comparison. And these are the manufacturing parameters there. The main difference is that in the nylon, in the short carbon fiber nylon, we're talking about a single extrusion. I forgot to mention we are using FDM in this study. In the continuous carbon fibers, we need to have double extrusions. In this case, we used commercial printers, Markforged Mark II, Ultimaker 2. Okay, this is a comparison then about the pros and cons of these two structures based on the literature, based on prior work in the group and beyond. So this is what one should expect. When we're talking about the performance in quasi-static test, we should expect the continuous carbon fiber composite to perform better, a couple of times better, at least that's what literature suggests. Complexity, single extrusion, complex extrusion, faster, much faster indeed. The cost is very significant. So if we are to go commercial in these materials, you see a factor of 10 there. The quality, these short carbon fiber composites are prone to defects, and we have lots of discussion about defects, and also warping. So if you are to print a large thin plate, like a tile for protection or an arbor, this needs to be taken into consideration. Nevertheless, there are ways to overcome it, but it adds in complexity. Volume fraction, as I said, limited as per the manufacturer, so there are other types of composites that come, say, with 10% or 30%. Here it's down to the user, okay? Some results. So I thought, since there's no relevant talk on polymer-based composites in this session, to include some quasi-static tests first. So let me start from standard tensile testing, ASTM given here. We're using this type of the specimen, 2 millimeter thickness, testing speed as shown there. Typical fracture in the gauge length, very good reproducibility in these tests. But let me go to the main message here. So you see, from now on, the color code would be red for the continuous carbon fiber, black for the short carbon fiber. So as it's been written here, the continuous carbon fiber has a higher tensile modulus. Actually, let me reveal the numbers as well there, and strength, but elongation is much less. The fracture is brittle, so if I populate all these graphs here, you can see some exposed fibers for fiber pull out. Okay, I would say the bonding seems to be weak between the fibers and the matrix. Moving to the compressive test, similar structure. You see this cuboidal. I'm only presenting results for the longitudinal cases here. We have done transverse cases, concentric, and so on. If we look again at the performance, in this case, the short carbon fiber has a higher compression strength, as you can see over here, since obviously it has a high volume fraction. The compression modulus is lower, however, compared to this continuous carbon fiber. Okay, let me now move to some dynamic results. We also perform dynamic mechanical analysis. This is the setup of the DMA. This is the specimen we have used, 64, 13, 3 millimeters of thickness. And we have performed a frequency sweep from 0 to 100 hertz. These are our results from these investigations. So in this plot on the left, we have plotted together the storage and loss moduli. With the dashed lines are the loss moduli for both structures. So what we see is that the storage modulus of the continuous carbon fiber, this is the line, is much, much higher than the short carbon fiber one. Now, due to the low fiber volume fraction, 10% versus 20, the loss modulus is slightly higher. You can see the dashed lines there. And on the right, we have this tan delta plot for both materials. We see that low values for the continuous one indicates mostly elastic behavior. Right, so with this, let me move to the ballistic. So this is our in-house gas gun that we have at Loughborough. Right here is our plate specimen, plate-like specimen, 100 by 100 and by 2 millimeters thickness to start this discussion. The bullet starts its journey from here, the projectile. In this case, we use a steel projectile of 9 millimeter diameter, traveling all the way. We have reduced this range. We have constrained this range to 100, from 100 to 120 meters per second. So these are some results. Post-mortem plates. Again, on the top is the short carbon fiber plate. On the bottom is the continuous one. This is the front side, this is the back side. The obvious one is both plates failed, okay? They did not perform very well with this thickness, complete perforation of this range. The damage is localized at the front, and then you see the lamination at the back. Here we have quantified these areas of damage. So as you see, the continuous carbon fiber has maybe half the damage area at the front and maybe half again at the back. Okay, so performs way better, even though the volume fraction of carbon is less. A bit of modeling. Again, this is ongoing work, so we replicate this with commercial software, Abacus namely. So we have a steel spherical projectile. We have the elastic properties. These are listed here. A few are estimated as well because we're lacking this information. And we have prepared a standard subroutine, a VU-mat in Abacus, incorporating these hashing damage criteria. These are listed here. Fiber fracture, tension and compression in blue and green. Matrix fracture, again, with the parameters listed on the right of the slide. We also try to incorporate the cohesive behavior among the printed layers. Here you see some videos coming up. So we have some surface bonding for traction separation, and we have tested this type of samples now, not the longitudinals, to estimate this layer separation as you see here. Essentially, we try to go from there to the standard bilinear traction separation law. The difference obviously is that with the cohesive you have smaller penetrated area. So I think this is my only slide for the ballistics modeling. On the top, the short carbon fiber composite. On the bottom, this is the continuous. Again, we replicated the complete perforation we saw experimentally. Circular hole here at the front, a bit of delamination at the back, so good, reasonable agreement. Here we have the comparison actually. So this would be the experiment, this would be the model. I would say the back side of the plate needs some work to match the experimental results. Before I go to the conclusion, and I don't want to finish this with a message that, look, these materials do not perform well. We have done further studies. Obviously, the choice is to increase the thickness, but before we do that, we can try different patterns. So the concentric and other patterns have performed way better than this one. So a bit of recap, tensile test, so this brittle behavior. The continuous carbon fiber composite had the higher strength and stiffness, but less ductility. Let me move here to the ballistic, localized damage with the circular hole, the lamination at the back, and our numerical modeling, as I say, is at a reasonable stage at this point and needs further calibration to explore and feedback to the manufacturing parameters. Okay, thank you so much.
Thank you very much.